Hello, class. We're going to start talking about 3.7. That is the exponential and log derivative chapter. If you're following along in the book at all, you'll notice that this is slightly out of order. I personally prefer to do this earlier. The book tends to do implicit differentiation and inverse trig functions before it does exponentials and logs. I do think exponentials and logs are a lot simpler than those, so my personal preference is to do these earlier. So I moved this chapter forward from 3.9 to 3.7. So if you notice any discrepancy, that is why. But we're going to start with the exponential. I really think this is a really great rule. It's going to be pretty straightforward, but I'm going to start us off by introducing how the rule is kind of derived, or like where it comes from. And so, as usual, when we start with a derivative we don't know, the first place you should always start is to find the limit definition, right? So we're going to take the derivative with respect to x of b to the x, okay? So remember, we're dealing with an exponential function. That is, you have a variable for the power and you have a constant for the base. It's kind of the opposite of a power function, which looks like this. So if you guys remember your power rule for power functions, you have a variable base to a constant power, and we do this. Unfortunately, for a problem like this with an exponential, we can't apply that rule, okay? This is not a power rule. It got its own rule. It's called an exponential rule. But as I said, we'll start with the limit definition. So we'll do the limit as h approaches 0 of b to the x plus h minus b to the x all over h. And I want to remind everybody that there is some algebra that we can leverage here, that if I have b to the x plus h, that I can actually rewrite that as b to the x times b to the h, okay? Remember, when you take a product of two exponentials where they have the same base but a different power, you add the powers, okay? So we're going to split this guy over here, and it's going to look like limit as h approaches 0 of b to the x, b to the h, minus b to the x all over h, okay? And so we're slowly working our way toward trying to figure out what the derivative of b to the x is. Now, we do have a GCF now. If you guys will notice here, I have b to the x twice. And so my next step, I'm going to factor that out. I'm going to go, hey, I can pull my b to the x out. And so I'll be left with b to the h minus 1 all over h. There is one more thing that we're going to do here. And so I want everybody to recognize that this b to the x right here, it has no h's in it, right? So when we take a limit with respect to h of a b to the x term with no h in it, this limit does not affect this b to the x. And so in fact, I'm going to go even further, and I'm going to pull out this b to the x, okay? So I'm going to have b to the x times, the limit as h approaches 0, of b to the h minus 1 all over h. And let me write what we're finding. This is the derivative of b to the x. Okay? Now, here's the idea. I don't know yet, and neither do you, what exactly this term right here is, right? But this is going to be some number, right? Could be 1, could be 0, could be -2. I don't know. You don't know. We don't know what this number is, but it is some number, okay? This limit should exist. There's no reason it won't. Right now it's going to 0 over 0, so, but it shouldn't be doing anything funky like going to infinity or doing anything strange like that, right? Like, I don't exactly know what that's going to do, but it should be some finite number. And so the idea here is that the derivative with respect to x of b to the x is equal to some number times b to the x, right? And that's pretty cool. This is a really interesting thing. This is really unique. The exponential's derivative is proportional to itself. B to the x, when you find its rate of change, is some number times whatever it is. So in other words, this is b to the x, this is b to the x. Its rate of change is proportional to itself, right? So it might be, this might be a half, or it might be 2 times, or we don't know, right? There's going to be some number there. But this is really why exponential derivatives are really nice. When you take a derivative of an exponential, you always get that exponential back in your answer. Okay, so I started with b to the x. My derivative will also contain b to the x. Now, the really kind of concern then is what is this number? And we'll work our way towards determining what that number is in this chapter. But the first way that we're going to solve this is actually just by doing this numerically, okay? So you can pick an h that's small, and you can pick a b, and so we're going to pick several b's and small h's and try and figure out what's going on. Whatever this number is, right? I don't know what it is. Could be any number. And that's what we'll do on the next page, okay? So I'm going to go ahead and start sliding this down. We're going to look at what the next page is, right? So I have some tables here. I have done this. You guys could watch me punch this in a calculator if you're interested, but I don't think you are. So I've just computed these numbers prior to this session. And so here I have picked, right here, you guys will notice there's a 2. So this is really b equal 2. There's a 3 there. So this is really b equals 3. And so I've just chosen those two. And I chose them deliberately because they're pretty close to 1. If we're talking about integer b values, these are the two closest integers where we get a number that's somewhere close to 1 for that number that we're finding. Remember this right here, this term right here and this term right here, those are the limits that we were just speaking about up here, right? Like that's this limit right here in this red box or this red circle thing. And so when we look at the results, when we pick b equals 2 and b equals 3, that this number is trending towards 69315, and when b is equal to 3, that number is trending to 1.09862. Now, what's really interesting here is, and I hope you guys will agree with me, that between 2 and 3, there ought to be a number, okay? I don't know what this number is yet. We'll give it a name in a moment, such that this limit that we're doing is 1. So that is, if I have whatever that number is, I don't know what it is yet, but if I do this, that should equal 1. And I don't know what that number is, but it should be between 2 and 3, because at 2, that limit is less than 1, and at 3, that limit is greater than 1. So somewhere between 2 and 3, we should hit a number where that limit is exactly equal to 1. And that's going to form the foundation of our exponential, okay? So coming back over here, this term right here, I haven't named it yet, but this limit is really the f prime of 0, okay? So this limit that we've been dealing with, where we have limit as h approaches 0 of b to the h minus 1 over h, that is f prime of 0, okay? We don't know exactly what f prime is, but we do know that this is what that would be at 0, because f of x is equal to b to the x. And so that means that f of 0 is equal to 1, right? And so this formula right here is really just the formula that you would do for the derivative at 0, okay? And so we know that f prime of 0 for 2, this is b equals 2, is going to approach 0.69315. And for b equals 3, f prime of 0 is going to approach 1.09862. And again, in between these two numbers is 1. And so the question is, what number will give us 1? And the really interesting thing is, we don't, you can figure this out like using numerics and like using computer simulations. It's really easy to figure out what this number is. But we already, at the point that calculus was derived, they didn't know what this number was. They did a lot of work to try to figure out what it was. And it turns out when they did that work, they discovered it was another number that they had dealt with before. And we usually call that E, okay? Euler's number is another phrase for this. Like if you look it up on Wikipedia, this is often called Euler's number. He was the first person, Leonard Euler, to start talking about this letter E. And so you guys have seen this before. It comes out of interest rates and it comes out of population growth. Anything where you have exponential growth, we usually deal with the letter E. And so the letter E is that special number where this adjustment term for the derivative is 1, okay? So what's nice about this is that means that the derivative with respect to x of e to the x is going to equal e to the x times this limit as h approaches 0 of e to the h minus 1 over h. And by design, this e number we're choosing is going to make this thing right here equal to 1, right? we're choosing e such that this thing right here is 1, which means that the derivative with respect to x of e to the x is just e to the x, right? Because this thing right here goes to 1. And so this will be the foundational rule that we'll use for exponential derivatives, that the derivative of e to the x is e to the x. And it's really, really nice. It's so nice. If you have an exponential function and you're taking its derivative, you just get that function back. And then, you're going to have to do product rule, you're going to have to do chain rule, all those normal things. But the rule for the exponential part of it, gloriously simple. It's just going to be itself. Okay, here are some graphs that illustrate this a little further. So here is 2 to the x. This blue graph right here is 2 to the x. This darker graph right here is 3 to the x. And the one in the middle is this e to the x right here. Okay, so it's sandwiched between them. And if we just look at e to the x, it has this really nice property where when x is equal to 0, it has a slope of 1. And in general, if you look at any other value of x, the slope is always just e to the x. Okay, so in other words, this is again the statement, if the slope is e to the x, this is the statement that f prime of x is e to the x for the original function e to the x. Okay, so its rate of change is proportional to itself. It's pretty nice. Very nice. I have that rule written one more time right here. I will write it another time in kind of the notation that we've used for other rules here, where the derivative of e to the x is equal to e to the x. Okay, very nice. Now, as I said, we've learned product rule, we've learned quotient rule, we've learned chain rule. So you're not going to see any derivative that's this simple, right? We gotta spice it up a little bit. So the first one we're going to do is going to be e to the tan of 2x. Okay, so I want to take the derivative with respect to x of e to the tan of 2x. Okay, and when we're talking about chain rule here, remember we got to think about this in terms of layers. So the tan is inside the exponential, so the exponential function will be my first layer, and then I'll have a tan, and then I'll have a 2x. Okay, so this is an intermediate level chain rule, and we're going to do the first layer. My f of we'll call it something else. Sorry, so we'll call f of x. And let me change my labeling here. So we'll call this g of h of x, right? And so g is the exponential function, e to the x, and g prime of that is really straightforward. It's just e to the x again. So when I take this derivative, I'm going to get e to the tan of 2x, exactly the same, with no changes. But I must handle the chain rule. I must handle the inside layer. So I'm going to multiply that by the derivative of the inside. What is the inside in this problem? Well, the next layer down is tan of 2x, so I'm going to put tan of 2x here. Now, when I do tan of 2x, that's another chain rule, okay? I'm going to pause, give you guys about 5 seconds here where I'm not going to say anything. I want you guys to pause the video, and I want you to try and see if you can do the derivative of tan of 2x yourself as another practice to remind yourself of how to do chain rule. And then when you unpause, you can see me do it, okay? So I'll give you guys 5 seconds. Okay, hopefully you paused and tried this yourself. Let's go through it. So when we have e to the tan of 2x, we're going to put that to the side. We're going to keep track of it, but we're not doing any work with it. I need to take the derivative of tan. So my h of x in this problem is tan x. Well, in fact, it's tan of 2x. And so when I do h prime of x, I need to know what the derivative of tan is, right? And so for our sake, I will give you guys the rule one more time, but I do expect you guys to know this by now. Tan x is secant squared x, right? So when I do this derivative, I know I'm going to get secant squared of 2x, and then I am going to have to multiply by the derivative of the inside, right? What is the derivative of 2x? That's a 2. So I'm going to multiply by the derivative of 2x here. And so coming down here, I'm going to have secant squared of 2x times, what's the derivative of 2x? 2. Okay? And so we'll put all this together. My f prime of x, to bring the 2 up front, I'm going to write 2 e to the tan of 2x, secant squared 2x. Okay? And try to be careful with your writing. You don't want to make it look like your secant squared is in the power. So you'll notice I wrote tan a little smaller and I wrote it above just to make sure there's no confusion about what is where. I personally prefer to write my exponentials before my trig functions, but some people do prefer it the other way. So if you wrote the exponential on this side, that would be okay. All right. That is an intermediate level chain rule, though. There's 2 layers to this problem, or rather, there's 3 layers and 2 chain rules to this problem. Let's see, what's my next one? Okay, I do have another one. So we're going to go ahead and move on to example 43. And I'm going to give this one a try as well. And so this is another intermediate level chain rule with a quotient rule in it, right? So we can do g of x is equal to e to the x squared over x. And I have a top function, I'm going to call it t of x, which is e to the x squared. I have a bottom function, which is just equal to x. And so below this, I'm going to go ahead and do the work for the derivative of e to the x squared. Okay, I want to figure out what t prime of x is, the derivative of the top, and I want to just be able to write that above, so I'm going to do the work for it below. Like b prime I can do really straightforwardly. The derivative of x is 1, but this is going to require some work because this is a chain rule. So recall, the derivative with respect to x of e to the x is e to the x, so we'll just use that rule, but it's no longer e to the x, it's e to the x squared, and then we multiply by the adjustment term from chain rule, derivative with respect to x of x squared. What is that? Well, we bring the 2 down and we subtract 1. So I'm going to bring this 2 down. 2 minus 1 is 1. So this is really 2x e to the x squared. This is really 2x e to the x squared. And so over here, when I do g prime of x, I'm going to do my quotient rule. And so we're going to set up our quotient rule by following, I have this structured in this way, where we're going to go like this diagonally left, and then let me switch colors, we'll go diagonally right like this. And so I'll make sure I write the one going toward the left on the left, the one going toward the right on the right. So I have 2x e to the x squared times x, and then I have a minus between them, and I've deliberately followed my trajectories here so that I have the correct order on my quotient rule. But I'm going to have e to the x squared times 1. I do have a denominator for quotient rule. That is going to be the denominator squared. In this case, my denominator is x, so I'm just going to put an x squared there. So g prime of x is equal to 2x squared e to the x squared minus e to the x squared all over x squared. I personally prefer to factor when I have common terms like this. So I'm going to write this as 2x squared minus 1 times e to the x squared all over x squared. And that is a perfectly fine final answer. We can take this just a little bit further if you'd like to simplify this further. We can do that. And so how would we do that? Well, we could split the fraction. So we could write this as 2x squared over x squared minus 1 over x squared times e to the x squared. And so in that case, we would end up with 2 minus x to the minus 2 e to the x squared. Okay, that's probably the cleanest final answer. But again, I'm not going to worry too much if you didn't notice or do this work. This is a perfectly valid final answer. I just think that's a little cleaner. So that would be my personal preference. But again, totally up to you whether you are noticing or have the time in an exam or quiz environment to do all that algebra. Okay. If you need to keep writing, if I'm a little ahead of you, you're welcome to pause here. But I do have one more example. We're going to do a real world problem with a colony of mosquitoes. And so that is example 44. And then I'll go ahead and end the video there, and we'll do one more on base B. So let's talk about a colony of mosquitoes. We have this colony of mosquitoes. It's growing according to the formula 100e to the 0.25t. This is probably too small. I actually don't have any real idea how fast a colony of mosquitoes grows. So I was pretty conservative with this function. We're starting with 100 mosquitoes, and t is measured in weeks. And so we want to show that the ratio of the rate of change of the population to the population itself is a constant, okay? That's a lot of words that may confuse you. So let's start breaking this down. When we talk about the rate of change, that's the derivative. So when I say the rate of change of population, this is p prime of t, the derivative of the population. The population itself is just a way of referencing P of t. Okay. Now, the word ratio, when you guys hear the word ratio, you want to think about dividing two quantities. So I'm specifically interested in the ratio of the rate of change to the population. That means I'm interested in P prime of t over P of t. Okay, that's really what I'm talking about when you hear the word ratio. Usually we express ratios as fractions. So if you have, if you're half the height of your brother, you would say, the ratio of your height to his height is 1/2. Okay, that's kind of what we're saying. 1 to 2 would be another way to think about it, but we usually frame this in terms of fractions. So we need P prime of t. Let's try to figure out what that is. P prime of t is the derivative with respect to t. We're using t not x of 100 e to the 0.25t. This is a constant multiple rule, so we'll pull that out of the derivative here. And so I have e to the 0.25t, and I know how to take that derivative, right? The derivative of an exponential is itself. So this is 100 e to the 0.25t, and then we do chain rule. I have to take the derivative of the exponential part, the inside, that is 0.25t. And so we're going to get 100 times 0.25. Derivative of t is 1. And then the exponential is exactly the same. Okay. 0.25 is a quarter. A quarter of 100 is 25. Okay. That's our P prime of t. And so up here, bringing it back to our ratio is going to be equal to 25 e to the 0.25t all over the original function, which coming up here is 100 e to the 0.25t. Naturally, you have exponentials on the top and bottom that are identical. They're going to reduce. And so the ratio is really just 25 to 100. That is a quarter to a dollar, or in other words, 1/4. Okay? So what is this saying? This is saying that every week, the population is going to grow by a quarter of itself. So if you start with 100 mosquitoes, after a week, you're going to have 125 mosquitoes. And then after another week, you're going to have, what's a quarter of 125? That's like 30 more, give or take a few decimal places there. So you're going to have 155 after 2 weeks. And then you're going to do another 25%, right? So like that's what this ratio is really telling us, is that the because of the ratio of the rate of change to the growth, because the ratio of the rate of change of population to the population itself is a quarter, that means it grows by a quarter every week. Okay? And so the population grows by 1/4 every week. Now, if you've ever lived in a muggy place or visited like New Orleans or Florida, this is probably conservative. I bet you populations of mosquitoes grow far faster than this, to be honest with you. But of course, I'm not factoring in the fact that if any real model would include the fact that there's a max sustainable population where like at some point the mosquitoes will stop growing simply because there's not enough fresh water sources, or there's not enough food, whatever factor is affecting their growth. It is going to cap sometime. But you can kind of think about the population, and if we started with 100, then we'll go to 125, and then let me get out my calculator. We can put down a couple more numbers just to kind of see how this scales. You guys are interested here. So we're going to do 100 times 1.25 is 125, times 1.25 is 156. So I was a little off. I called it 150. It's actually 156.25, but you can't have a quarter of a mosquito. And then 195, and then 244, and so on, okay? So after like 5 weeks, we'll have 3 times as many mosquitoes if you started with 100. This is actually, 305. So you guys get the idea. Again, that's probably way too conservative. I bet they grow much faster than that, but I just was trying to give you guys a real world problem, and I was being very conservative with the growth rate here. Okay. I'm going to go ahead and stop the video here. We'll talk about doing base B exponentials in the next video, and then I'll do another video for logarithms, okay? So please check out the next video when you feel ready to talk about some non-E base exponentials. Like if we have 2 to the x or 5 to the x, we'll talk about how to do that next.